Welcome to ChemExam Explained, where the aim is chemistry clarity, exam mastery. In today's video, we will be looking at CSEC Chemistry, May-June 2011, Question 1. This is a data analysis question. Let's go. A group of students conducted an investigation to determine the products of electrolysis when copper 2 sulfate was electrolyzed using copper electrodes. The following steps indicate the procedure they used. First, the copper cathode was first washed in distilled water, dried and weighed, and then connected to a suitable circuit. Secondly, a current of 0.2 amperes was passed through the solution and the starting time recorded. Thirdly, after 5 minutes, the switch was turned off and the cathode was removed, rinsed with distilled water, dried in air, and then weighed. The fourth step, the cathode was returned to the circuit and the process was repeated, recording the mass of cathode at 5-minute intervals. After each interval, the cathode was rinsed in distilled water, dried in air, and weighed until a total of 5 readings was taken. And finally, this shows you the table of the mass of cathode and the mass for 3 of the 5 readings. So you can see that at time 0, the mass of the cathode was 11.80 grams, which means that no copper was deposited at the cathode. After 5 minutes, the mass of the cathode went to 11.83 grams. And as you can see then, if you subtract 11.80 from 11.83, you get 0.03 grams. So that was the mass of copper deposited at the cathode after 5 minutes. We will do the same thing at 5-minute intervals for up to 25 minutes, and we will put in the missing information. We will calculate that in part 4 of the question. Let's just look at a simple diagram of what is going on here. You have your electrolysis setup, and you have your connecting wires with your ammeter and your cell, and we have here a resistor. This part, being the positive side of the battery or the cell, makes this electrode the anode. This side, being the negative side of the cell, makes this electrode the cathode. So if we have copper as the anode and the electrolyte is copper 2 sulfate, then this is an active electrolysis process where the anode of copper atoms will break down into solution to form copper ions, and then at the cathode, copper ions will then form copper atoms at the cathode. And you should observe that the anode gets smaller while the cathode gets larger. Here I put the Faraday's laws that we should know because it contributes to what is going on here in the electrolysis process. So Faraday's first law states that the mass of a substance liberated during electrolysis is directly proportional to the quantity of electricity used. That means more electricity is required to produce more substances electronically. And the second law states that 1 mole of various atoms is liberated by 1 or more moles of electrons. So we have 1 mole of sodium liberating 1 mole of electron. We have 1 mole of calcium liberating 2 moles of electrons. And we have 1 mole of aluminum liberating 3 moles of electrons. And each mole of electrons would affect the Faraday's constant. So sodium, which is 1 mole of electron, would liberate 96500 coulombs. Calcium liberating 2 moles of electrons would be 2 times Faraday's constant, and aluminum liberating 3 moles of electrons would be 3 times Faraday's constant. Let's continue. A part 1. Define the term electrolysis. Electrolysis is the process by which electrolytes are decomposed by an electric current. Or you could say that it is the chemical decomposition of an electrolyte by the passage of an electric current. 1A Part 2. State two differences between the anode and the cathode. So here we have three, you can use any two. At the anode is the positive electrode, and ions migrate towards the anode, and oxidation takes place at the anode. For the cathode is the negative electrode. Cations migrate towards the cathode, and reduction takes place at the cathode. 1A Part 3. Draw a diagram to show a circuit for carrying out this investigation. Label the cathode and the electrolyte. So here we have our diagram, and we have our container containing the electrolyte copper 2 sulfate. We have the anode at the positive side of the battery, and we have the cathode at the negative side of the battery. We have our connecting wires, and we have a lamp, or we could use an ammeter that shows us that our circuit is on or it is working. And so your diagram must have a label for the cathode, which we have here, copper as the cathode, and the electrolyte is copper 2 sulfate. 1A Part 4. Complete Table 1 by recording the mass of the cathode after 10 minutes and 20 minutes, and the mass of copper deposited after 15 and 25 minutes. So let's go with the first part, looking at the cathode after 10 and 20 minutes. So let's first look at the mass of the cathode after 10 minutes and 20 minutes. So if you notice, at time 0 minutes, we have a mass of the cathode to be 11.80 grams. But after 10 minutes, that space was blank, so we have to fill in that information. But what do we have? We have the actual mass of copper deposited to be 0.05 grams. Therefore, all we need to do is to add the 11.80 with the 0.05 grams to get a mass of 11.85 grams after 10 minutes. To find the mass after 20 minutes, we do the same thing. We add 11.80 to the actual mass deposited of 0.09 grams to get 11.89 grams at the cathode. Now, in order to find the mass of copper deposited after 15 and 25 minutes, we come to 15 and 25, where we now need to find the actual mass deposited. And so in order to do that, we simply subtract 11.80 from the mass of 11.87. And so we get 0.07 grams deposited at the cathode. And we do the same thing for 25 minutes, where we are subtracting 11.80 from 11.97, and we get the mass of 0.11 grams. And that completes our table. Let's continue. 1A Part 5. Plot a graph of actual mass of copper deposited versus time using the axis in Figure 1 on page 5. If we come back here, we're going to be plotting this actual mass of copper deposited, and this will be placed on the y-axis, and time will be placed on the x-axis. So this is our graph. On the x-axis here, we have our time, and on the y-axis, we have the actual mass of copper deposited. Let's look at the x-axis. Here we have 1, 2, 3, 4, 5 centimeters, and we have 10 units for every 5 centimeters. And so that is simply saying that for every centimeter, that will be 2 units. So we go 2, 4, 6, 8, 10, and so on. Now, on the y-axis, the graph was broken so that we have between 0.03 and 0.04, we have 0.01. So between each of these figures, so every 2 centimeter will go 0.01 all the way up to the top here. So if we want to find out what is the value of one small box, we simply divide 0.01 by 10, and that gives us 1 times 10 to the minus 3. So looking at part 6, if we are to use the graph to predict the mass of copper that would be deposited after 28 minutes, we would come to the x-axis, find 28 minutes. We're going to interpolate until we touch our line, and then we're going to interpolate across to the x-axis. And so if we have 0.12 grams and we have 2 small boxes to the red line, then we're going to add 1 times 10 to the minus 3 plus 1 times 10 to the minus 3 to the 0.12 grams, and we'll end up with a value of 0.122 grams. For part 7, we are to write an ionic equation to represent the reaction at the cathode. So we have our equation here, and remember, we have copper 2+ ions in the electrolyte that is going to migrate towards the cathode, forming copper solid. And so when we have reduction taking place, you have electrons being gained to the ions to form copper atom, and that is what increased the mass at the cathode. 1a part 8. Calculate the quantity of electricity that passed through the copper sulfate solution when 0.2 amperes of current flowed for 20 minutes. Here we were given the quantity of electricity is equal to the current times time, and 1 Faraday is equal to 96500 coulombs. So the first thing we're going to do is to write down the information we have, and we have the current. So we have the current equal to 0.2 amperes. Our time was in minutes, so we must convert minutes to seconds, and we do so by multiplying 20 minutes by 60. And so 20 by 60 give us 1,200 seconds. Now we're going to use the equation Q equal IT, which is Faraday's first law. So our current of 0.02 amperes times 1,200 seconds gives us the quantity to be 240 ampere second. Now remember, 1 ampere second equal 1 coulomb. So this should be a capital C. So 1 ampere equal 1 coulomb. So the quantity of electricity is 240 coulombs. 1a part 9. Calculate the number of moles of copper that would be formed. So in answering this question, we must start with the half equation. The half equation will tell us what is going on based on Faraday's second law, that 1 mole of copper ion would liberate 2 moles of electrons. So that is important for the calculation. So this is the half equation. So after we set up our proportion method, we say that 1 mole of copper would liberate 2 times 96500 coulombs based on the number of electrons produced or liberated. So if 1 mole of copper produced 2 times 96500 coulomb, so how many moles would be needed to produce 240 coulombs? So we're going to cross multiply by saying 240 coulombs times 1 mole is equal to 2 times 96500 coulombs times x. And then we're going to make x the subject of the formula. So x is really equal to 240 coulombs divided by 2 times 96500 coulombs. And so we're going to now divide 240 moles by 193,000 coulombs. And that gives us a value of 1.24 times 10 to the minus 3 moles of copper. So this is the moles of copper that would be needed to produce 240 coulombs. 1a part 10. Calculate the mass of copper that would be formed. And so we're given the relative atomic mass of copper to be 64. And for every Faraday, we get 96500 coulomb. So from that, we can find the number of moles of copper by simply saying number of moles is equal to mass divided by molar mass. So mole is equal to mass divided by molar mass. and we want to find the mass. Therefore, mass is equal to moles times molar mass. And so from that, the mole that was calculated was 1.24 times 10 to the minus 3 times the molar mass of copper, which gives us 0.079 grams of copper produced. Now remember that if they did not ask for the moles directly and they wanted to find the mass, we could simply use 64 grams of copper, which is the mass of 1 mole of copper, produced 2 times 96500 coulombs. Therefore, X grams of copper would produce 240 coulombs, and we'd find X in grams. And that would give us the mass of copper formed, which is 0.079 grams. Part 11. Suggest a reason for the difference between the mass of copper obtained in Part 10 above and that recorded in Table 1. So if you look at what the procedure was talking about, the mass obtained in the table for 20 minutes was given to be 0.09 grams. So here we have 20 minutes and the mass deposited was 0.09 grams. But the calculated value, we just calculated the value in Part 10, that was 0.079. So you can see that the calculated value is less than the value given in the table. So the higher weighted mass of 0.09 grams compared to the lower calculated mass of 0.079 grams could be that the electrode was not completely dried, and that could be a result of that mass difference. Another possible reason could be the fluctuations in the current during the electrolysis process, and this could cause a higher mass to be deposited. 1A, Part 12. The circuit used in this experiment was modified by replacing the copper electrodes with graphite electrodes. State one difference in the reaction at the anode when graphite electrodes are used. So remember now, if we are using an electrolyte, for example, copper 2 sulfate, and our anode is copper, that is, it is a metal of the electrolyte or the salt, then that would be active electrolysis. But if we replace the active anode with graphite, now it is not an active electrode, and therefore factor 1 must come into play, which is looking at our electrolyte as aqueous and our electrodes as inert. And so let's look at the differences. In the first instant, the copper anode would break down from atom to ion and get smaller. If we're using the graphite as the anode, now we'd have OH minus ions migrating towards the anode, liberating oxygen gas. So oxygen gas will be produced at the anode instead of the formation of copper ions going into the electrolytes. Secondly, no change in the mass of the anode would occur. Since the copper would not be present, then the copper atom would not disintegrate into the solution to form copper ions. 1B. Complete Table 2 by writing the observations for the test carried out on salt S. Let's look at the test and the inference so we can make the correct observation. A sample of salt S is heated strongly in a dry test tube. Moist, red, and blue litmus is held at the mouth of the test tube. The inference is an acidic gas is produced. So once we're using moist, red, and blue litmus paper, we are testing for acidity or alkalinity. Because the gas is acidic, it will change the blue litmus to red, but there will be no change in the red litmus. That is important for you to say both. For the other inference, nitrate ions are present. And when nitrate ions are present, it produces NO2 gas. And NO2 gas is a brown gas. So the nitrate ions are the reason for the brown gas. For the second test, to an aqueous solution of salt S, aqueous sodium hydroxide is added gradually until in excess. The inference is that zinc ions are present. Well, let's write zinc ions, lead 2 plus ions, and aluminum 3 plus ions. They all produce the hydroxides. Zinc hydroxide, lead 2 hydroxide, and aluminum hydroxide. Now, these hydroxides are all amphoteric. So after reacting with the sodium hydroxide to produce zinc hydroxide, lead 2 hydroxide, aluminum hydroxide, that will give you the white precipitate. The excess sodium hydroxide would cause them to dissolve because they are all amphoteric. This is the end of CSEC Chemistry, May-June 2011, question 1. Please remember to like, subscribe, and click the notification bell so that when new videos are uploaded, you will be notified. Thank you.